Thank you very much. First of all, I would like to thank the organizers for this opportunity to present the work done with my colleague Tomáš Blažek and two students, Jan Ramaj and Martina Sabová. It's an honor for us, and it's also a challenge because I'm going to talk about things to non-physicist audience, basically. So I decided to spend most of the time by motivating the questions we dealt with, and only in the end I will present some of our results. So when you look to the right, you can see a huge telescope. It has a hyperbolic primary mirror here in the lowest part of a diameter like 4 meters in diameter. And on the top, you can see the focal plane where they put 5,000 optical fibers, taking the light from the focal plane to spectroscopes, so they can at once make 5,000 spectra of galaxies. I think the exposure is like 2 minutes. And why they are doing so? Because when you know the spectrum of galaxy, you know the redshift and you know the distance from the Hubble law, and you can make a three-dimensional map of the universe. So this is a small section of the data. First data release contained like 7 million of galaxies, and they will go up to 35 million, I think. And why I'm showing this is that, okay, there are different type of galaxies. This is extremely random, this pointer, but what I want to say that it is very homogeneous. It may not appear so because you see the colors, but this is just because when you are looking to more distant part of universe, you are restricted to see only special types of galaxies. So the green part is from quasars. The most distant part is like 7 gigaparsecs, which is roughly 23 billions of light years. It is the cosmic distance, so the look-back time or time when the photons were radiated, we are now detecting is 12 billion of years. So it is not in conflict with the age of the universe. So the main point is that it is very homogeneous. The black parts are due to the galactic plane, our galaxy shields, the look to the distance, this more distant part of the universe. But when you have, okay, this was the main point, at cosmological scales, which is some megaparsecs, some hundreds of megaparsecs, you see a homogeneous and anisotropic universe. This is an important thing. It is called cosmological principle. And when you imagine that you are a homogeneous, you are yourself a homogeneous and isotropic universe, the only thing you can do actually is expansion or collapse. Otherwise, you would break the homogeneity or isotropy. So from the data, we know that our universe expands, but for non-physicists, this does not mean that our bodies, the world, as the galaxies do not expand themselves. The expansion is only the solution of Einstein equations or Friedman equations at a very large scale. So we assume basically that the universe is filled with a perfect fluid. And we solve the equation of motions for such thing. So when you have expanding universe, what happens to particles that are otherwise streaming freely is that they slow down. And if they are massless, like photons, they of course travel by the speed of light, but they stretch their wavelengths with the scaling factor A. So when A is 2, that means that all the distances are scaled by a factor of 2, all the areas by A squared, which is 4, and all the volumes by a factor of 8, and so on. And that's the thing that when you measure the redshift, you measure how much the photon wavelength stretched, and you can calculate where it was radiated, how far away. Okay, here in the right corner we have Friedman equation, which is basically the equation that allows us to predict how the universe expands. The rho here is the energy density. So of course the speed of expansion or of the expansion rate depends on how much energy we have in the universe. And we have 3 types of energy in the universe. First of them is the most mysterious one. This is the cosmological constant term, or dark energy. And we have almost no idea what it is. When we calculate such quantity in standard model of particle physics, we get something that is 120 orders in magnitude bigger, which is quite a wrong prediction. So it's a big unknown today, and kind of controversial. There was a Nobel Prize for accelerated expansion of universe in 2011, but recently there are 2 papers published in quite good journal that are showing that this could be just an effect of misunderstanding how supernovae type A work. So maybe we will see some revision of this paradigm, but what is more solid is the understanding of these 2 remaining terms R. The second is the simplest to understand, which is ordinary matter. So we have pressureless particles like atoms or dark matter also. And when you expand the universe by a factor of something, the volume will be something cubed bigger, and the density and energy density is divided by 8 to 3. And the last part is the radiation part. Today we have just photons and neutrinos in this radiation category, and it gets one more power of A because of stretching the wavelengths and losing the energy because of this. So there is usually in the Friedmann equation people write also the curvature term if they want to be too general, but in our universe what we know from experiment is that the curvature is completely negligible. There is a mechanism to explain that, which I will not talk about. Today's value of the expansion rate, dAdt over A, is 67.7 kilometers per second per megaparsec. So if you have a galaxy that is several megaparsecs, like 1 megaparsec is 3 million of light years away from us, it should have a velocity due to the expansion of 67 kilometers per second. It is not always so simple because galaxies also have their own peculiar motion. For example, the galaxy in Andromeda is moving towards us, even though it is at roughly the same distance, like 1 megaparsec or so. Okay, so this is the picture of the energy composition. So the mysterious dark energy is today almost 70%, which we completely don't understand. Then there is roughly 26% of cold dark matter. I will tell you more in a while. And then we have 4% or 5% of atoms, mostly hydrogen, and a bit of helium and lithium and heavier elements. So why cold dark matter? Because apart from the dark energy that accelerates the universe, we also have observations of relative motion of galaxies in clusters and the rotation of galaxies, the rotational speeds of stars around the galactic centers. And also other observations point towards the need of more matter than what we see in terms of hydrogen in stars and in some dark clouds and so on. So it seems from many independent sources that we need more matter than we can observe today in the universe. And unfortunately, we have no explanation for that from the particle physics point of view. Okay. What I showed you first was a relatively complicated dependence of the energy density from the universe expansion, from the scaling parameter. But at some early times, like 10 to 50,000 years after the Big Bang, which corresponds to A equal 10 to minus 4. So everything at this time was 10 to minus 4 times closer than now. At this time, the radiation part, which is today completely negligible, was dominant. And in such case, we can make an approximation that the energy density depends just on radiation. This happened, this crossover, that the radiation becomes radiation dominated, happened at temperatures at times 50,000 years after the Big Bang, which corresponds to the temperature of the plasma in the universe, 10 to 4 keV, and in our favorite units it is 0.25 electron volts. And at this time, the universe was expanding proportional to square root of time. So this is good to have in mind, that the universe expands still and cools down. And what is important, that the large-scale structure that is also negligible on very large scales, but some fibers of galaxies and galaxy clusters and all of this was not formed yet. So at this period, during the radiation-dominated era, the universe is very homogeneous, hot and dense, soup of all possible particles. Okay, when we speak of particles, let us imagine a collision of two proton and antiproton. So when we are talking about particles and radiation-dominated era, we can think about some chemistry during this period of time in the universe. Chemistry that in the sense that we describe this period in terms of some reactions of particles that are created there. So we have the annihilation of proton and antiproton, and the most favorite final state for this reaction is creation of three pions. Pions are light bound states of quarks and antiquarks. Three types of them are there, and we can also have reversal of this interaction. So if everything is hot and dense, and then we have this reaction in both directions in time. There is a subtle thing that protons were not always there. These are also bound states of quarks, and they only formed roughly at 150 MeV, so just below the proton mass. But once the protons are formed, the co-moving density, which is the number of protons per cubic meter times A cubed. Otherwise, I would be sensitive to the expansion of the universe, and I only want to understand how the proton density evolves. Then the proton density will decrease with increasing temperature. Why? Because we have not enough energy. Pions have not enough energy to create proton-antiproton pairs, but proton-antiproton pairs can annihilate into pions. So we will lose proton-antiproton pairs. And at some point, the protons and antiprotons will be so diluted in the universe that they cannot hit each other, and their density will freeze out, which is observed here. The value of A today is 1, so we can see that if this is how things happen, we have proton density 10 to minus 10 proton per cubic meter. And what do we observe, if I can go back in time here, is that we have overall, we have density that is roughly 5 protons per cubic meter, and 5% of that is roughly 1/4 of proton per cubic meters, is average baryon density today. So we are roughly, if this was the case, and this is a prediction of the standard model, this curve, this prediction of the standard model, then we should have 9 orders of magnitude less baryonic or matter or protons than we observe today. So we would not be here, basically. So yet another motivation for a new physics. So summing that all up, we have, this is the standard model of particle interactions that is well working for describing particles at colliders like LHC. There are some quarks, which are here, up and down form protons and neutrons, and the others are heavier copies that are very unstable and decay to the light quarks. Then we have electron and heavier copies, and 3 neutrinos, photons responsible for electromagnetic interactions, gluons for strong interactions, W, Z, and H. H is the Higgs boson, and W and Z are heavy particles responsible for electropic interactions. But this fails to explain the dark matter, because there is no heavy, stable, neutral particle. The only massive neutral particle here is Higgs, which is too unstable. It only lives 10 to minus 22 seconds, which is quite unstable. And then we are not even able to explain the baryonic matter we see. So there is some discrepancy between what we know from studying particle reactions at colliders and what we know from cosmology. And this is good motivation for people to think about some extension of the standard model. And if we have such extension, it cannot have too strong interactions with the standard model part, because otherwise we would observe it very easily in our universe, which is not the case. But it also cannot be completely decoupled. Like gravitational interactions are not enough, because otherwise we would not be able to explain why the density of dark matter and baryonic matter are roughly of the same order. If they are completely independent, there could be orders of magnitude differences. So this coincidence has to be also explained. So the question is how to extend the standard model to get correct baryon number density and correct dark matter density in a natural way without needing some fine-tuning of parameters. That's also an important technical point. And for the second thing, the baryon asymmetry explanation, which is much more technically difficult. There are 3 conditions known for many years, like from 51, I think. This is 91 because it was published in English. This is the link to English paper, but it is, I think, in the 60s. It was published first by Sakharov. And the conditions are that we need some reactions, like in chemistry, that produce or, let's say, produce baryons. That means that we have no baryonic particles in the initial state, no protons, no neutrons, and we produce them somehow. So this is the baryon number violation, very, very simplified way. Then we have some discrete symmetries in any quantum field theory, let's say. That is a charge conjugation which exchanges particles and antiparticles. Parity operation which changes vectors to minus vectors, which is up to rotation, the same as changing left and right. And then we have a time reversal. And from all of these, there is a funny thing that none of the discrete symmetries is symmetry of our nature. Each of them is broken, at least in the electroweak interactions. But under very robust assumptions like space-time symmetries, which means that the laws of nature should be invariant under translations, rotations, and relativistic boosts. And the theory should be local, so causality should be respected. Then such theory should be CPT symmetric. And to produce baryon asymmetry, we need independent C and CP symmetry violation. C is automatically done in standard model, but unfortunately CP is very difficult. And there is also some CP violation, combined CP violation in the standard model, but it is like many orders of magnitude too weak. And then we need interactions out of thermal equilibrium, which means that you have, imagine 2 bodies that are in contact with each other. They are sufficiently isolated to maintain different temperatures. That is an example of what it means to be out of thermal equilibrium. And it is also easily fulfilled by assuming the interactions with the standard model sector are weak enough. Okay, so how it is done in practice, and now it will be more technical, so I will try to do my best, but don't be surprised if you don't understand everything. It has been shown that you do not need to generate the baryon asymmetry from the beginning. It is enough to generate lepton number asymmetry, so slightly more electrons than positrons. And then some high temperature interactions in the standard model can convert this partially to the baryon asymmetry. And this scenario is called leptogenesis because you first play with leptons and then baryons are automatically done. And the easiest way to do this is to introduce some very heavy neutral fermions N. These are also called heavy neutrinos, which are like 10 to 10 mass of proton, let's say. And this can decay either to leptons and Higgs's or to anti-leptons and anti-Higgs's. And we define some ratios which measure how many these decays you have per unit volume per unit time. And this reaction rate for decays to leptons is slightly bigger than to anti-leptons. So this decay would produce slightly more leptons, let's say. But things are not so easy because when you have such a theory, it automatically and necessarily implies that you have also scatterings lepton Higgs into anti-lepton anti-Higgs, which produces opposite asymmetry. So in equilibrium, these two processes cancel each other. And you have no asymmetry in the end, in the density of leptons. So you need the departure from equilibrium for this, which happens when the temperature drops below the heavy neutrino mass. Then the decays will be somehow more efficient, and you will produce the asymmetry. Unfortunately, in this leptogenesis seesaw Taiwan model, you will not have a dark matter candidate because these heavy neutrinos are unstable and they decay quickly. So you have no dark matter. And there are 2 types of approaches in the literature. First, and much more common, is that you look for some problems, technical problems of particle physics theory, some tuning or naturalness. You want to explain neutrino masses. And so you come with some idea of a new symmetry. Like supersymmetry was a very famous candidate. Some bigger symmetries of interactions, which are called grand unified theories. Some multiple Higgs bosons. Everything you can play with, you can introduce new particles, and you will get dark matter and leptogenesis or directly baryogenesis, and you are happy, but your theory contains many new particles and many new parameters and so on. And then there is so-called bottom-up approach, that you play with something that is called effective theory. This is a type of theory that is, in a sense, incomplete, but it is okay because you suppose it is valid. You only suppose it is valid under some very high energy scale, and then you expand your quantities when you are computing early universe stuff in powers of temperature over that scale. So it will converge somehow. And this is what we actually did in our paper. I was supposed to talk about. So this is the last slide showing some of our results, and this is the Lagrangian density for those who can read it. And it basically has just two parameter couplings, which you can think about some analogy of electric charge or electromagnetic coupling. And this is this lambda prime and lambda, where lambda couples the new dark sector particles into standard model lepton and Higgses. This is called the portal operator or portal interaction. And then you have something what many particle physicists know as Weinberg operator. The Weinberg operator that is, after the electroweak symmetry breakdown, is responsible for natural generation of very light neutrino masses. And what is interesting in this case that what people were used to do when dealing with the asymmetric reactions were just decays and in a very low number of papers also scattering, asymmetric scattering 2-to-2 reactions. But in a natural way, in this model, even so simple model, we showed that it is necessary to include some peculiar or special reactions, like the 3-to-3 reactions, where the state of scalar S remains unchanged. So you have basically lepton Higgs to antilepton anti-Higgs scattering, but you need a spectator particle there. This is something that is somehow difficult to come to, but the theory shows that you need to include such processes, otherwise everything would be inconsistent and you will break the Sakharov conditions easily. So thank you for your attention, and I look forward to your questions. And if you want to know more details about the asymmetric generation, you can see our poster and I will be there and happy to answer your questions. So thank you very much.